Hi everyone, welcome back. Advanced Organic Chemistry 3120. Today's lecture 14, and we're going to look at cross condensation. So we completed lecture 13, the Aldol reaction. Cross condensation. So, as the name implies, we looked at self-condensation for the Aldol reaction last lecture. This one's going to involve two different species, and it's going to be up to us to figure out what the product is and how to control that. So let's get right into it. So in this case, we're going to have two different carbonyl compounds. Two different carbonyls. So what are they? Okay, so we have this ketone and then this aldehyde. It's like this paranitro benzaldehyde. And we treat this with sodium hydroxide with water and ethanol. The question is, what is the major product? Okay, so first thing you want to do is look for acidic protons whenever you're doing an aldol reaction. So look throughout all these molecules and look for alpha protons. Now we just have one type of alpha proton, and that is right here. Right? There are no alpha protons on the aldehyde. So your OH minus can pick that up, form an enolate, and then once that enolate's formed, it's nucleophilic, so where is it going to react? Well, you have the aldehyde there, so you can imagine this will come and react at the aldehyde, like I'm showing you here. This carbon-carbon is your new carbon-carbon bond. And then this will pick up a proton from water to generate your neutral aldol product. And then if we asked you to dehydrate it, you know you're going to remove this, again, this acidic proton under basic conditions. You're going to go through the conjugate base. We went through that mechanism last lecture. And then the electrons come down, form and move that double bond, and remove that hydroxide group. So your dehydrated product will look like this. I forgot my nitro group. Okay, so any questions, right? There's an example of a cross condensation. But question you might have is, well, why didn't this molecule here react with a molecule of itself? Right? Because the previous lecture I taught you that electrons could come down, but it could also react with the starting ketone molecule. Now it turns out if you actually do this reaction, that's going to be your single product or definitely your major product. And you're not going to observe condensation between the two ketones. Only condensation between the enolate of the ketone and the aldehyde. So why is that? Think about that for a few seconds. I know we're not doing this in real time, but I'll tell you the answer. Keep thinking. What did you think about it? Let's compare electrophilicity, right? So if you thought of electrophilicity, which one's more electrophilic, the aldehyde or the ketone? The aldehyde is more electrophilic, right? So naturally, this enolate is going to react at the more electrophilic molecule, so you don't have to worry about it reacting here. Less electrophilic ketones are less electrophilic compared to aldehydes. So in this case, it's fairly straightforward in terms of one single product through two different starting materials. We call this type of analysis, or this type of reaction, equilibrium control of the Aldol reaction. Really what this means is that you add the two components together in one pot at the same time, and you let equilibrium and thermodynamics dictate what will be the major product. So the two species, so in this case aldehyde and aldehyde, or aldehyde and ketone, ester and aldehyde, you just add those two together. I'll say together in one pot simultaneously. And the major product formed is due to, I'll say, things like thermodynamics, and just fundamental electronics and chemistry, so electrophilicity, and I would say the laws of fundamental organic chemistry. Hope you can see that. And the major product form is due to thermodynamics and fundamental organic chemistry. Okay, so this example that we've done right here is an example of equilibrium control of the Aldol reaction. Let's go through a retrosynthesis, and I'm going to ask you to make this compound here. So rather than going through the mechanism and telling me what the product is, here's the final product. How are you going to make it? Synthesize the compound via Aldol reaction. Okay, so now we need to work backwards, right? We need to figure out a few different things. We need to figure out what our key carbon-carbon bond is. And you can see here that it looks like a dehydrated aldol. So work backwards. So you know that if this is a dehydrated aldol, it once had water attached to it. And it had water attached through removal of this double bond, having an alpha proton here attached to the aldehyde, and then an OH group here. Okay, so I would say step one, identify the key carbon-carbon bond. Okay, so that's right here. And then step two, if it's dehydrated, identify what the structure of the non-dehydrated aldol will look like. what does a non-dehydrated molecule look like? So draw it out, right? So actually draw it out exactly what that will look like. And make sure you talk to yourself, right? If you're doing this class, definitely follow along, but when you're studying on your own or with people, actually talk it out. You know, just close your door or don't worry about it and just talk. Just say, I know that there must have been an acidic proton here and there must have been OH here, right? Convince yourself that this is indeed the case. So there's your alpha proton and there's a hydroxyl group. So you can see that it makes sense of how it was dehydrated. And this is still your T carbon-carbon bond. And then step 3 is going to be identify your nucleophile and your electrophile. So did the reaction form this way or did it form this way? All right, so if you formed the carbon-carbon bond this way, this must have been an enolate. Electrons would have come down, and then this must have been a double bond, and this would have reacted at like a carbonyl center. So this portion here must be your nucleophile, right? Must have been the nucleophile, whereas this area here must have been the electrophile. You can't do it the other way, right? You can't form an enolate here and have that react at that carbon. That carbon is not electrophilic. So again, have these conversations with yourself. And once you establish what the nucleophile and electrophile are, establish not where, but how about which species are the nucleophile plus electrophile. And then you can draw those out. So let's draw those out. So you can see that your electrophile is going to be this portion here. I apologize. The nucleophile. See, this is why you have to talk to yourself so you can correct yourself. The nucleophile will be this species here. Once you convert it to an enolate, it will be nucleophilic. And then the electrophile is this before it got attacked. So it has to be this carbonyl ketone here. As I'm showing you here. Okay, so that's the process you want to work on in order to figure out what your molecular components are. Once you do that, you have your electrophile, you have your nucleophile, then you can mix them together, right? So let's try that. Let's mix them together. You say, aha, nucleophile, electrophile, bingo. So let's put in our aldehyde plus this molecule here is called benzophenone. And you can use sodium hydroxide, water, ethanol, because it worked for that one. You put these two together, mix them up, go for lunch. However, when you come back, you notice that you don't actually generate that species. And let's not forget heat here. What do you think we actually make? And you're a little confused because you learned that, this is not enolizable, so that's actually really good. This can only act as an electrophile. So this is your only enolizable molecule. So this, when it reacts, forms this enolate. However, when this comes down and acts as a nucleophile, this doesn't actually react here. Where is it going to react? it's actually going to react with another molecule, the aldehyde. And that's because aldehydes, as we just talked about over here, are much more electrophilic. So before you can even try to convince this to react with benzophenone, unfortunately this will react with a molecule of itself to generate this, and then this will dehydrate to form that. And that's not what you want, right? You want to make this. This is actually the first product we made when we started this lecture, last lecture, lecture 13. So in other words, you're just getting self-condensation, and this molecule here is just watching. It's just a spectator molecule, enjoying the fine reaction of these two molecules. So how do you solve this problem? Well, I told you about equilibrium control of the aldol reaction. We just mix them together, walk away, and just let equilibrium and thermodynamics determine what you're going to make. But in this case here, we need to actually control the order and addition of molecules so we don't get that self-condensation. And remember, we talked about last chapter, chapter 25, aldehydes, they're just so prone to self-condensation because they are just so darn electrophilic. And how did we solve that problem last chapter? We learned how to alkylate aldehydes, but we learned how to alkylate them using something called a specific enol equivalent. So what we can do is we can actually convert this aldehyde to something different where it will not self-condense, but it's still nucleophilic and enolizable and can react at the desired molecule. So I'll tell you how we do that, but it's going to build upon some of the fundamentals we learned last chapter, in chapter 25. Before we do that, let me just make just a quick note about what I just said. So, can't mix everything together because aldehydes are too electrophilic, so self-condensation occurs and the ketone will not react. So what we're going to do is we're going to step this out into several different steps. We're not going to mix everything together. So let's start with our aldehyde. And let's convert this to a strong nucleophile, but we don't want it to self-condense. So we're going to convert this to something called an aza-enolate. And recall, with aza-enolate formation, you need to react this with a primary amine with catalytic protons. So let's just call this H2NR prime. Okay, so if you do that, you generate an imine, and then the second step, you need to convert that imine to an aza-enolate. So in that case, you need to use a strong base. So a good strong base would be something like LDA. And once you have that aza-enolate, which is strongly nucleophilic, then you can add your electrophile. You don't need to worry about self-condensation because you converted all of your aldehyde to an aza-enolate, so there's no more electrophile present until you add the ketone. So the aza-enolate reacts with the ketone, and then you'll be left with an imine back at the molecule, and you need to hydrolyze that imine. And a good way to do that is simple hydrolysis of the imine with water and acid. So you really should be able to go through all these mechanisms, right? And if you struggle a little bit or need some help, then I urge you after this lecture to on your own go through it and check back with some of the fundamental notes from chapter 25. Talk to your peers, talk to me. That's what the course packs are for, set up in time with me. But I would expect you to be able to know how to do that. So if you do this reaction together, you will generate, and let's add some heat, you will generate your product. So let's draw out that product again. Okay, so just make a note here, this is the desired product. And if you mix these all two together on the top, like I'm showing you here, if you actually do that reaction, this is your undesired major product. Okay, same starting materials, approach is very, very different. So, the first time we looked at this, it was called equilibrium control of the Aldol reaction. This one is called directed control of the Aldol reaction. And I'll just write a couple words about what that means. But what we've done right there is an example of directed control of the Aldol reaction. And as the name implies, you're directly controlling which components you're adding, which and when, so that you don't get, you don't get the undesired major product based on the rules of which one is more electrophilic, which one is more nucleophilic. You control that. So directed Aldol reaction. So let's write this. One component is converted to a specific enol equivalent, like we've done there, through azaenolate, and only then is it combined with its electrophilic partner. And as I mentioned, that's an example of directed Aldol approach. Okay, hope you enjoyed this lecture on cross condensations. We're going to end this lecture for now and then actually really focus on specific enol equivalents in the Aldol reaction next lecture. Okay, see you in a little bit.